So some students have confusion about why this is true. And I think some students think that there should be a factor of half on the right-hand side. So let me repeat why we did this. So when we discuss Hartree-Fock theory, so what have we done? What does this statement really does? It replaces product of 4 operators by a bunch of terms that contains only 2 operators. These terms are organized in 2 lines on the right-hand side. The first line is the Hartree term, and the second line is the Fock term. So when we discuss Hartree-Fock theory, we said the reason we write this as sum of Hartree term and the Fock term is because of Wick's theorem. So let me repeat for clarity. There is no other factor of half here. And let me show it why. So what is Wick's theorem? So we showed this in class. So this we derived in class. You can check your notes. Now all you have to do to see this is take expectation value in the top line on both sides. When you take expectation value on both sides, left-hand side becomes this, right-hand side becomes this. One of these will cancel with this, one of these will cancel with this, and you will get precisely the result you expect from Wick's theorem. If you only include the Hartree term, you will, and not the Fock term, if you only have the Hartree term, you violate Wick's theorem. If you only have Fock term, you violate Wick's theorem. If you multiply a factor of half on the right-hand side, you violate Wick's theorem. So the reason we replaced the 4 operator term by a bunch of 2 operator terms and call them Hartree term and Fock term in this way is so that our result is in agreement with Wick's theorem. Okay, so with this clarification, I would now continue the discussion of phonons. So by end of this lecture, I hope I can convince you that you can use theory of phonons to explain experimental data that you can measure specific heat for solids as a function of temperature. Now, at room temperature or higher temperatures, you don't need to do a quantum theory, and you can understand the result by simply equipartition theorem, and the specific heat is just a constant. And we already discussed this yesterday, just from elementary thermodynamics. So what we are going to do next is, so we also discussed classical theory of phonons yesterday, and we saw that essentially we just have to solve for normal modes of bunch of point particles, some massive particles connected by springs. So now what we are going to do is, our goal is to develop a quantum theory for phonons. So let's start with just, let's show it once. What we really want to do is a very simple calculation. So we have a 1D lattice, and the position of the jth ion is Rj. So Rj is the coordinate for the jth ion. Rj minus 1 is A, which is lattice constant. N is total number, so the total length is N times A, where capital N is the total number of ions. The displacement of each of the ion is Uj. So Uj is the displacement. So what I'm going to do is put vectors here. And so these are the locations of coordinates of the ions at equilibrium. These capital R's, and U's are the displacement from their equilibrium position. So now, yesterday we worked with the Lagrangian, discussed the equations of motion, and calculated the dispersion relation for phonons. We want to now quantize them. So we first write down the Hamiltonian. It's very simple. We have just the kinetic energy for all of these. So sum over J from 1 to n. We have momentum square by 2m. For simplicity, I'm assuming all ions are identical. They have mass capital M. And also all of the springs are the same. So what are these spring constants? They are basically second derivatives. So the sum is, so they are second derivatives of the interaction potential between ions calculated at the equilibrium separation between the ions. So it's k by 2 uj minus 1 square. Any questions so far? So in quantum theory, what we would expect is these U's and P's to have the commutator relations, which are, this is what we would expect. So there are many ways to see this. You have learned this in your quantum course. So the position and momentum operators, they satisfy this commutation relation. Next, we are also going to impose periodic boundary conditions. That means the displacement of n plus first ion is same as the displacement of the first ion. Imposing this periodic boundary conditions would imply that you now have discrete values of k, small k. So imposing this periodic boundary conditions. So before we do that, let's discuss that because the system is periodic, it would be very useful to go to Fourier representation. So when we go to Fourier representation, let me define, this is momentum, Fourier transform of momentum. And let's just define it with square root of n. Sum n varies from 1 to capital N, e to the power minus IKAN Pn. And similarly, I will define Fourier transform of the displacement operator. Now, imposing periodic boundary conditions implies that this k can only take discrete values now, and these discrete values will choose to be in the first Brillouin zone between minus pi by a to pi by a. These discrete values are given by 2 pi divided by total length, which we'll write as capital NA times some integer m. And this integer m is from minus n by 2 to n by 2. So this we have discussed many times earlier, so I'm just using the result. So from this, you can also define inverse Fourier transform. So the calculation is pretty straightforward other than a minus sign. So I'm going to focus on that minus sign only. So this is the inverse Fourier transform, right? It's just inverting that equation. Next, what I'm going to write down is this term sum over j varies from 1 to capital N pj square over 2m. So this is simply 1 over capital N sum over J sum over K, K prime e to the power I K plus K prime A J pi K prime over 2m. Now this sum over J will give you a delta function. That means K is equal to minus K prime, or K prime equal to minus K. So what this term gives you is sum over K pi minus K over 2m. Any questions? So you can do the same calculation for this term. Now because you have e to the power I j minus 1, there will be additional factors of e to the power I k a involved, and you can go through the calculation. You will see that they can be combined in the form of cosine, and the final result is k by 2 sum over j from 1 to n uj minus uj minus 1 whole square can be written as k by 2 sum over k for sine square ka by 2. Again, you have qk and q minus k. This, I will write it as half m omega k square where I will use that omega k is square root 4k over m mod sine ka by 2. This is same as the dispersion you calculated using the classical equations of motion. So this looks extremely similar. This looks very familiar. This looks similar to the Hamiltonian for simple harmonic oscillator. Actually, bunch of similar harmonic oscillators, each harmonic oscillator being labeled by K. How many values of K are there? Capital N. So there are capital N harmonic oscillators. And each of these harmonic oscillators have a frequency given by omega K or omega, and for K, substitute this value, 2 pi times the small integer m divided by Na. So these are frequencies of these harmonic oscillators, and you have capital N of these. Now, interestingly, you would see, so the only difference for the moment is this K and minus K. Otherwise, it looks very familiar. So there is a trick we can use to, so this K or minus K does not play any relevant role in the physics, because we are going to absorb this definition in our definition of creation and annihilation operators. You'll see this in a minute. You can think of this as a symmetry. So if you have a symmetric system such that K and minus K states are symmetric, and this is usually, so if you break some symmetry, it could have, if you break this symmetry, you could have some implications coming from this. And if there will be some implication, you would see this in the commutation relations. So what do I mean by that? What I mean by that is, so far we have defined these Q's and P's. Let's calculate this commutator Q, K1, pi k2. If I calculate this commutator, I get 1 over n this you can show that this is simply 1 over n sum over j prime e to the power minus I k1 a j e to the power minus I k2 a j, and now you have I h bar delta j prime. So what this commutator gives us is I h bar delta k1 minus k2. So this is the physical significance, or this is the importance of that minus sign. So now when you write down commutators, be careful of this sign here. Now typically we are going to work with not these momentum and position operators, but we want to use the second quantized notation, creation and annihilation operators. So that's what we are going to do next. And what we'll try to do is absorb this, get rid of this, or define the creation and annihilation operators in a way that their commutator does not have this negative sign. And after that, we can use the usual tricks that we learn, and everything will be good and fine. Yes?
For the sum and the phonons,
Yeah, I'm sorry, I did like, right? Yeah. Any other questions? Okay, so let's do this next. So the way I will do this is I will define the annihilation operator as 1 over square root of 2 qk divided by some length k plus I pi k divided by h bar over some length k, and I will define b of minus k dagger as complex conjugate of this. So this side is just complex conjugate of this line. The only thing is I've defined that complex conjugate as b minus k dagger, where Lk is some length, which is for each k is given by the usual frequency of the simple harmonic oscillator. So we'll see that this definition what does that give us? So using this definition, you can write down that qk, q of minus k. So you can calculate q of k by adding them, and similarly you can calculate q of minus k, and so you can solve those two equations and write qk in terms of bk and b minus k daggers. And what you will find is that qk, q minus k, is lk square by 2 bk plus b minus k dagger, and b of minus k plus bk dagger. So this would imply that this whole thing half m omega k square qk q minus k, this simply becomes h bar omega k by 4 bk b minus k plus b minus k dagger b minus k plus bk dagger. I think it should be minus, oh, yeah, bk dagger, and the last term with b minus k dagger bk dagger. Similarly, you can do the same calculation and show that pi of k and pi of minus k over 2m, this will be written as minus h bar omega k over 4 b of k, b of minus k, minus b minus k dagger, b minus k, when you add everything, you can show that the total Hamiltonian will become sum over k. You can add both terms, and in this minus k, relabel the minus k to k, and note that omega of minus k is same as omega of k. So in this sum over k for Hamiltonian, you can rewrite this total Hamiltonian as h bar omega k bk dagger bk plus half. So where we relabel minus k to k and use that omega of minus k is equal to omega of k. So from these definitions, you can also now calculate commutator of bk1 and bk2 dagger, and you will find that this commutator now is simply delta k1 k2. So we've gone through this pretty straightforward calculation. You can do all the steps. Details are in the notes. You'll see that there is some issue coming from a minus sign, but it can be easily resolved by defining the creation and annihilation operators in that manner. And now we have a quantum description of sound, which is basically a bunch of harmonic oscillators with frequencies omega k. And these k values are given by 2 pi divided by capital Na multiplied by integer m. Now, what happens for k going to 0? For k going to 0, we discussed yesterday. So omega k is defined over there. It's given by modulus sine ka by 2. So as k goes to 0, omega k goes to 0 linearly with k, and that means that you have waves that correspond to sound waves in the classical regime, and this is the quantum description of them. Now, you can do similar calculation, which I'm not going to do here. Now, for this system, where you have two types of ions, and you will find that, again, you can quantize this, everything works out. What you will find is that now, again, you have creation and annihilation operators, but now you will have, for each k, you will have two modes. So for each mode, you have creation and annihilation operator. When you do this, you'll find that you will have another index which will be in these creation and annihilation operators, which will refer to which branch it is, whether it's acoustic or optical. Now, this is 1D. You can do it in 3D. In 3D, you'll find that there are 3 acoustic branches. This doesn't look very symmetric, but please imagine that it's a symmetric function. So in 3D, you will have 3 acoustic branches and 3 optical branches. So the reason for this is in 3 dimensions, you can have sound waves moving in all 3 directions. Another important concept that emerges when you have more than 1 dimensions, which you will do in the homework problem, I think, is the concept of polarization, where the displacement of ions can be different from their direction of motion. So there's a vector polarization that gives you the direction of displacement of the ions. So in 1 dimension, everything is straightforward. There's only 1 direction. Ions can vibrate and the wave can propagate. But there are straightforward extensions of these concepts in higher dimensions. Any questions so far? So next what we are going to discuss is called Debye model. And this is a model that explains the behavior of specific heat for solids as a function of temperature. So let's first discuss what Debye model really does. So we have such dispersion relation. And in 3 dimensions, so this is, let's say this is our dispersion relation for phonons. So what is plotted here is just omega as a function of k in the first Brillouin zone. What Debye model says, is that replace all this by a straight line like this and a straight line like this. Now you go beyond the first Brillouin zone and you go till a wave vector defined as kd, which is the Debye wave vector. So essentially what Debye model is doing is you can try to flip this optical branch, use an extended zone scheme to show the dispersion relation. And it says this optical branch I'm going to ignore and I'm just going to extend this linear branch and assume that it accounts for the optical mode. Also, the acoustic mode, the dispersion is really sinusoidal. You have sine function, and you're placing this whole thing by a linear function. So this seems like a very crude approximation. But again, this does indeed work out. Actually, so this should really go all the way till there. Okay. So this is the approximation. Replace 2 branches. So you have optical branches and acoustic branches. Replace both of them by 1 branch, which is all linear, and it goes from 0 to Debye momentum kd. So the dispersion relation for this Debye mode, now you have only 1 branch, is omega k is some velocity. Let's call it Debye velocity. Okay. Now in 3 dimensions, you will have different acoustic, you'll have 3 acoustic modes, and you will have 3 optical modes. Now, in 1 dimension, you have an acoustic mode where the velocity, so this slope of this linear curve is same as the velocity close to k equal to 0 of this white line, of this original dispersion. Now, it's possible that different modes in different dimensions have different velocities. So in general, you will have dispersion omega k lambda is v lambda times k, where lambda goes from 1 to d. In 2 dimensions, you will have 2 such modes. So in 3 dimensions, you have 6 modes, but in Debye approximations, these will become 3 modes, right? Because we got rid of optical modes altogether. So in the d dimensions, in general, you will have this. Now let's make another simplification. We have already ignored so many things. In the same spirit, let's ignore even more structure in the problem, which is replace all these velocities, v lambda, say velocity in x direction and velocity in y direction, velocity in z direction, by some average which we call Debye velocity. So replace this by the Debye velocity. So there's h bar here, h bar, velocity, and wave vector k. Any questions?
Is the cutoff KD related to the properties of the material we have, or we can choose like?
Yes. So that's what we are going to discuss next. So what is this KD? This does depend on properties of the material. One way to see is, let's assume that the total number of ions is this capital N ions here. So we want our approximation to represent or to cover all of these ions. So this total number of ions is, I'm going to write this, should be equal to volume. So we figure out what Debye frequency is, or sorry, Debye wave vector is, by assuming that all the k states that are included till kd should be able to accommodate all of the ions. So the total number of ions is same as volume in k space divided by volume of each state. So we did this in first week, volume in k space. Now we have an extremely simple model. We've discarded any discrepancy between velocities. We just have a sphere of radius Debye momentum. So the volume in k space is simply 4 by 3 pi Debye momentum cube. The volume of each state in phase space is simply 2 pi cube divided by the total volume of the system. So you can find out that kd, the Debye wave vector, is 6 pi square total number of ions divided by omega to the power 1 by 3.
How do you know it's bigger than pi over a?
Bigger than pi over a. So now if you want to put it this, so it really depends on, let me see if I can prove it right away. So if you have, so one easy way to see it is the number of k states here in the acoustic branch will be replaced. There will, for each point, you need an energy, right, for each k mode. So till here is accounted for here. but you have to account for optical branch, so this has to go beyond the first Brillouin zone. But I think you can try to write down a model just for acoustic branch and then show that mathematically that this is greater than pi over a. Any other questions? So now using this Debye wave vector, you can define Debye temperature and Debye frequency. So h bar Debye frequency is same as the Boltzmann constant times Debye temperature, and this is same as h bar Debye velocity times the Debye wave vector. Just like we define density of states for electrons, we can define density of states for phonons. And in the tutorial today, you will do this exercise. What another useful formula for density of states is to first define the density, which is number of ions by omega, and then calculate density of states using dn over de. You can see that this n can be written, this total number of ions can be written in terms of kd, and this h bar vd kd can be written as energy, and then you can calculate this derivative. You will find that the density of states is epsilon square 2 pi square h bar Debye velocity cube. For so you can see that the density of states is very different as compared to the electronic case. For the electronic case, you showed in tutorial yesterday that you get square root of E in 3D. The density of state goes as square root of E. Here, the density of state goes as square of the energy. So these are very different spectrums that we are talking about. Here we are talking about phonons. Any questions? Yes. So when we did, so this calculation is similar to when we did the free electron gas. So what we assume is everything is symmetric in this description. So you think of kx, ky, kz space, and you draw all the quantized wave vectors imposing periodic boundary conditions, and you'll find that the distance. So what is the distance between two neighboring k values here is 2 pi over na, sorry. Similarly, 2 pi over length in x. That is the difference between two k vectors, right? Similarly, difference between two k vectors in y is 2 pi over ly, then 2 pi over lz. So in 3D, the volume becomes 2 pi over the total volume. Any other questions? Okay, so next, now we have all we need to do our calculation. So in the tutorial today, you'll derive this, you'll use this, and also there will be some integrals involved in our calculation that I'm not going to do here, and you will do those integrals in the tutorial. So our goal is to calculate the energy of the lattice as a function of temperature. So what we want to do is calculate expectation value of the Hamiltonian, basically. So this can be written as sum over all occupied momentums, all occupied states, h bar omega k bk dagger bk plus half. So simply speaking, this is just expectation value of the number operator. So we really have to calculate expectation value of number operator. These operators B, commute, these are bosonic operators. So to calculate this occupation number, we can use the Bose-Einstein distribution function. Yes.
So why does this density of states depend on the energy? Because didn't we find that usually the density of states goes as like 1 over the derivative of energy with respect to wave vector?
Yeah, so that is the general description. But depending on your dispersion relation, you can have very different density of state. So we can understand this by taking an extreme example. So what density of state does is I give you an energy, and density of state tells you how many states are there for this available for occupation for this energy. Now imagine what does this mean? How many states? It means there are many values of k labeled states. There are many values of k that give us the same energy, right? So imagine that you have omega as a function of k, straight line. If I give you this value of energy, there are a lot of modes, a lot of k values. But if you have some other dispersion, the number of modes available for occupation would be less.
This is because we're working in 3 dimensions.
Yes, so you will get different expressions in different dimensions also. In the homework, there is a problem in 2 dimensions, and you will calculate the dispersion relation, and using that, you can calculate the density of states. So again, I think in this calculation also, we'll see this factor coming. So essentially, we have to calculate this expectation value of number operator. Now, this expectation value of number operators, this is given by the Bose-Einstein distribution function, which I'm writing like this. Now, in general, this is the formula, this is the Bose-Einstein statistics formula. But in general, you may have many energy states, or you may have degeneracy, additional degeneracies. So for a given energy state, if the degeneracy is, say, G epsilon, then you have to multiply this by G epsilon. So there is no such factor for Fermi statistics. It's bound by Pauli's exclusion principle. So think of this G epsilon as degeneracy of phonon modes. What does that mean? Is if I give you an energy, you can have sound waves corresponding to that energy propagating in X dimension, Y dimension, and Z dimension. So in this model, our degeneracy is simply 3. Yes?
Okay, so just to be clear, we're working in a system that it's 3-dimensional, but the displacements are just allowed to be in one direction.
So we are working in 3 dimensions, and we have a fully symmetric problem. So we are just doing we're going to assume the calculation is so we're just assuming it's fully symmetric.
Okay, so we can just consider it as 1-dimensional, but the density of states is still in 3 dimensions.
Yeah. So this additional factor is simply, you can think of it as also polarization. What this additional factor really means is for each energy, your momentum space is 3-dimensional, but for each energy, you can still have sound waves propagating in 3 dimensions. And whenever we have these momentum sums and integrals, we'll work in 3 dimensions. So this 3 is coming from the fact that we are in 3 dimensions. Yes?
Can I get back to the density of states?
Yes.
So we have this dn by d epsilon, but we're saying that, KD is some constant, some cutoff. And
Yeah.
we're differentiating that with respect to the energy.
So this is you'll do in tutorial. So you will have KD, but you will, because it's a fully symmetric system, you will think of H bar VD KD as some energy epsilon. So when you are calculating density of states, say at this energy, because it's a linear curve, everything is similar, it's spherically symmetric, the volume is simply H bar VD K, this value of K. So depending on what energy you have, so this N is, as you rightly said, this N is not a function of energy. That's your question, right?
Yeah.
So you will write down, using this expression, you can write down this function of energy by replacing H bar VD KD by some general energy E. So you will do this in tutorial today also. Tomorrow? Okay, so it's tomorrow. Any other questions? Okay, so let's go ahead with the calculation. So now CV, the specific heat, is d over dt of this quantity. Now this sum over k can be written as an integral in momentum space. So I have a three-dimensional momentum integral. And then I have this h bar omega k. And then I have the Bose-Einstein distribution function. Next, what I'm going to do is I'm going to rewrite this integral in slightly different way by introducing a delta function. So this, I just rewrote that formula. From here to there and converted sum over k to momentum, I have really just inserted a delta function. This epsilon k is equal to h bar omega k. So you can see that these two are identical, right? So next what I'm going to do is I'm going to change the order, and I'll see that the specific heat is the derivative of temperature, integral dE. You have omega d cube k Now, this is very familiar. What does this delta function is? If we look at this delta function together with this integral over k, what this is doing is it's counting how many epsilon k values have energy E. So there is no k dependence here. We can do this integral first, and this quantity is simply equal to density of states. So this quantity just becomes 3 d over dt omega integral dE rho E divided by So next, you're going to do this integral, and use this relation, and there's a bunch of algebraic steps involved. Details are in the notes, and I think the final integral you will do in the tutorial. You will find that this result, the result of this integration is 9 times number of ions times the Boltzmann constant. Then you have T divided by Debye temperature cube integral 0. So I'm just writing the last step. Where x is equal to beta times epsilon. So the specific heat is given by that expression. That integral you can evaluate, or you can evaluate analytically two extremes of this integral, and you will find that the specific heat, this is given by 12 divided by 5 pi to the power 4 n ions kV So what we have shown here is that for large temperatures, temperatures much larger than Debye temperature, you do get back the classical Dulong and Petit law. But for small temperatures, now you expect the specific heat to go to 0 in cubic way. One thing I should stress here is that we have so far included only ionic degrees of freedom in the specific heat. So this calculation gives you the contribution to the specific heat that comes from ions. Physically, what happens is at very low temperatures, so one is low temperature defined with respect to Debye temperature, and then one is, I'm going even, so imagine it's much, much lower, which is very close to absolute zero. Debye temperature could be of order of few hundred Kelvin. So if you're much, much smaller than Debye temperature, then it turns out that ions, the mobility of ions freeze out. It's very difficult for them to move. And if you measure specific heat of a solid at these very low temperatures, very close to absolute zero, the degrees of freedom that count, that heat up the system, are actually electrons. In this calculation, we have not included electronic contribution to the specific heat. So because the scales we are interested in for the moment are the scales related to Debye temperature. So much greater than Debye, you have the classical Dulong and Petit. Smaller, much smaller, you have T cube. At very, very low temperature, it turns out that this T cube vanishes very faster. So phononic contribution to specific heat vanishes very rapidly as compared to electronic contribution. And electronic contribution to specific heat is actually linear. We will see this in detail when we discuss superconductivity, as this is one way to explore the properties of materials. In an experiment, you measure a physically observable quantity as a function of temperature and see how it goes to zero at low temperatures and figure out what degrees of freedom are relevant for explaining the behavior in that temperature regime. So this only includes the ionic contribution to specific heat. So if you compare this with the experimental data, so here it's the specific heat divided by 3 times number of ions and the Boltzmann constant as a function of temperature divided by TD. What you will find is that the Debye model predicts something like this. So it goes as to 0 as T cube, and then it approaches this at very large temperatures. Now, there is another approximation that actually came before Debye, and that was a calculation by Einstein. If you use that approximation, so there are many models. The Einstein model, that behaves something like this. So this is Einstein model for specific heat. And this is Debye. So the Einstein model, it predicts that the specific heat goes to 0 exponentially. So it's very fast. It goes to 0 very rapidly. And this model came out first, and it was very successful in explaining that the specific heat, it's not going to be constant, but this quantum theory actually helps you in understanding the specific heat of solids, and it goes to 0 at lower temperatures. It should really vanish. Now, what is this Einstein model? In this Einstein model, you approximate, so I'm going to draw, in Einstein model, you're going to make a different approximation as compared to the Debye one. And what you will do in Einstein model is, so you have two, so you have acoustic mode and the optical mode. In the Einstein model, you will do this linear approximation, but you will do it only for the acoustic mode. So you will restrict it till and you will replace the optical mode by a constant. And this constant is called the Einstein frequency. So in Einstein model, you do the same linear approximation. Actually, Einstein model came first. He said, let's replace the acoustic branch by all linear curve and replace the Einstein model by a straight line. And using this approximation, you get this lower curve. And then Debye model, it said, instead of replacing this by horizontal line, I'm going to continue this beyond the first Brillouin zone. And this model was more successful or agrees with experiments, and you do see a cubic behavior at lower temperatures. Any questions? Yes?
What's the physical interpretation of the Debye temperature? How you can interpret this stuff?
So the physical meaning of this Debye temperature is really when the motion of the ions. So it's really the when you should start using quantum description for describing the ions. So it's a scale related to this. So Debye temperature. So if very large, a temperature is much larger than Debye, you should be happy with the classical theory of phonons. Physically, why Einstein model did not do as good is because in Einstein model, you're neglecting the dispersion of these optical modes altogether. What Debye said is that in solids, we know that optical modes still have some dispersion. So we're just going to continue this with linear approximation, and that improves the calculation. But Einstein model is still very useful if you have a solid which has nearly flat optical branch. So this type of approximations are very useful in condensed matter to simplify the calculation and still get a behavior which qualitatively agrees with the experiments. Any other questions? So more on this in the tutorial tomorrow. Next, our goal is to discuss electron-phonon interactions. So we talked about electrons, electron-electron interactions. We talked about phonons. We talked about ion-ion interactions. We talked about kinetic energy of ions. Next, we are going to talk about interaction between ions and electrons. And eventually, we want to look at interactions between electrons mediated by phonons. And our goal is to show that this interaction can be attractive and give rise to a bound state of two electrons. And this will lead us to superconductivity. So, any questions before we move on? Okay. So, this is the potential. It is a two-particle interaction, but now the two particles are not identical. One is electron and the other are ions. Small r is the electronic coordinate and capital R is the ionic coordinate. You can think of these as operators at the moment. Then you will later on we'll go to the position representation, and again we are going to assume that they are diagonal in position representation, and we'll use the same tricks that we learned in the first two lectures to write this down in second quantized notation and then explore this interaction further. So now I will write down this coordinate Rn, which now represents the ion by, so this is slightly different notation from what we did before, because in this we'll have a lot of other variables. So now let's not worry about phonons in the sense. So okay, so for the moment we're going to restrict. What the key idea is that this would be a single particle term for electrons and ions respectively. So even though this represents two particle interaction, this is relatively simple object. So I'm going to simplify notation. I'm going to use these zeros to denote equilibrium. So this Rn is simply Rn naught plus Un, where this is the equilibrium position of the ions. So next I'm going to use a Taylor expansion around these equilibrium points. Now keep in mind, I am calling this V, but this is not the ion-ion interaction. for ion-ion interaction, using ion-ion interaction, we can figure out these values of Rn naught. So now we know the equilibrium position of Rn naughts, and at those positions, the potential corresponding to ion-ion interaction, that potential is minimized there. But this is different potential. This is potential for interactions between electrons and ions. And now I'm Taylor expanding this potential. Now, this term is not minimized, but this term we have also seen. What is this term? This is interaction between electrons, and now ions are at their equilibrium position. So this gives rise to the whole block theory. So if you include this periodic potential, this is the periodic potential that we included when we did band theory. So electrons, this is the potential when ions are at their equilibrium position. So electrons will see this potential, and as a result of this periodic potential, you generate bands in the system and so on. So this we already have a feeling for. We have already understood this object. This object is new, and we are going to call this electron-phonon. We are going to call this Hamilton H electron-phonon. So this is minus. And now I'm going to write this in second quantization, and I will use momentum eigenstates K and K prime for my second quantization. So all I have to do, because these are single particle objects, they are relatively easy to express in second quantization. What I have to do is I have to calculate matrix elements in the basis states. So K prime sigma prime gradient Rn V R minus Rn evaluated at Rn equal to Rn naught. So what I have done is so this involves ionic coordinates, ionic operators, and electronic operators. What I have done here, going from here to here, is, so this is a single particle term for electrons and single particle terms for bosons. I have written down the electronic part of this interaction Hamiltonian in terms of single particle operators. How do we write? So details go back to the first two lectures. How do we write single particle terms? It's simply given by C dagger C times matrix element of the single particle operator, of the total single particle operator in that basis set. So this K sigma here, these represent the block bands. These represent the electronic wave functions. So we choose momentum eigenstates for our second quantization, but we include the fact that we have a periodic system. So if you are trying to recall the total single particle operator, this can be written as sum over K. Then you have a, so I'm not going to write down We did this in detail in the first 2 lectures. So just see the calculation, how you got this. And this really is the matrix, was the matrix element of electronic eigenstates, which were momentum eigenstates. And you calculated these matrix elements in position representation of the single particle operators. So what this is matrix element calculated for electronic eigenstates, and these k sigma, these are now block wave functions. Actually, let's call it blockets or block states. Any questions? Now, this calculation is slightly tricky, and that's because of this gradient operator. So we are going to deal with this gradient operator next. One thing you can notice is that nothing in this operator depends on sigma, on spin. So these two from here, you will get a delta function in spin, delta sigma, sigma prime for this matrix element, and you can use that to get rid of one of the sums, sigma prime. Any questions? And next, I'm going to position representation and calculate this matrix element. So in position representation, I can write down the electron-phonon Hamiltonian as minus sum over n un dot sum over k prime sigma integral d cube r phi k star. So now these are block wave functions. Any questions so far? So next, what I'm going to use is Bloch's theorem. So let's use some symmetry properties of these eigenstates. So what I know from Bloch's theorem is phi k r plus a direct lattice vector, which are in our notation is capital R and naught. This is e to the power I k R and naught times phi k. So using this, I can show that the matrix element K prime gradient Rn V R minus Rn this matrix element can be written as e to the power I k minus k prime dot Rn naught integral d cube r minus Rn naught pi k prime r minus Rn naught gradient Rn v r minus Rn naught, sorry, v r minus Rn evaluated at So what I've done is I've used Bloch's theorem. So in the integral, in the original integral, writing it as r d cube over electronic coordinate r, I replace r by r minus Rn naught, and this r minus Rn naught, I know. So this is same as d cube r. This is just a constant. This is same, I've accounted for this factor. This is actually same with this factor as phi k prime of r. This along with, so yes, this with the k factor is same as phi k r. This term, the potential is periodic. So Vr minus Rn, if you add or subtract a reciprocal lattice, it's periodic. So this is same as Vr minus Rn. So if you add r minus Rn minus Rn naught, that is same. So I've used that V r plus a reciprocal lattice vector or r minus a reciprocal lattice vector is same as V of r. Any questions? So I've just rewritten this matrix element in the following way. Now you would ask why. The reason is now you can see that nothing on this integral depends on n. So n comes, it's a function of the argument Rn, and it's the variable of integration. This can be written as e to the power I k minus k prime dot Rn naught times some quantity that we are calling skk prime. This skk prime does have a lot of information about the structure of the ion potential and ion electronic or the electronic wave functions, but it does not depend on small n, on the index corresponding to the sites. So what that means is you can pull this factor outside the sum over n, and that simplifies our calculation a lot. So now the electron phonon interaction is simply minus k prime sigma s k prime dot sum over n e to the power I k minus k prime dot Rn not un ck prime sigma dagger ck sigma. Any questions? So what is next is we want to write down these the displacement operators in terms of bosonic creation and annihilation operators. So we can do that. So we can write this Q. So we know that you can write UN as use those definitions of Fourier transforms. You can use the inverse to write down this as sum over k e to the power I k a n q k, and qk can be written as square root h bar over 2m omega k b minus k dagger plus bk. So when I put this here, I can see that we can write u in terms of b operators. What I'm going to do is I'm going to write a general form of this u that accounts for a three-dimensional material which may have bunch of branches, acoustic and phonon branches, and some polarization. So in general, you can write the displacement un is equal to 1 over square root of n sum over q and lambda, where q is this k which runs over the first Brillouin zone, and lambda is again a label for various branches. So okay, it's not related to this lambda. So lambda is runs over all branches. And I'm going to assume that each of these branches labeled by lambda have some polarization vector which I'm denoting by capital A lambda. So we almost have everything. We have this electron-phonon Hamiltonian. We see we have electronic operators here. We do have these bosonic operators also. Next is to put this displacement operator here. But what we also have is this e to the power, a lot of these plane wave factors. So now I'm going to use a trick which is very easy to show, and it's very useful trick worth going over. You can show that sum over all reciprocal lattice vectors, delta function k minus k prime comma minus g is equal to sum over g 1 over n sum over small n, which runs over number of lattice sides. This is over all reciprocal lattice vectors. E to the power I k minus k prime plus g dot Rn naught. You can see that this G is a reciprocal lattice vector, this direct lattice vector. This simply drops out. You have e to the power I k minus k prime sum over dotted with Rn. This just gives you a delta function. Right? So this you can easily show by rewriting this as this is also equal to 1 over n sum over g sum over n e to the power I k minus k prime dot Rn naught. Now this sum over n and 1 by n, this just gives you the delta function. So when we put this displacement operator back in here, there will be this plane wave factor that will be combined with this plane wave factor, and we'll write it as, and we'll use this trick. And finally, we can rewrite this electron-phonon Hamiltonian as 1 over square root of n sum over k q g lambda sigma, this s k plus q plus g dot polarization lambda square root h bar over 2 m omega lambda q b minus q lambda dagger plus b q lambda, and then you have c dagger k plus q plus g comma sigma c k sigma. So using this trick, when you combine all these plane wave factors, you will see that only k prime equal to k plus q plus g term survives. So what does this interaction really mean? It means that you can have an incoming electron with k sigma, and you can have an incoming phonon with q and say in branch lambda, and the original electron will now get scattered to a state k plus q plus g. So this is where you have this term, b term, where you destroy, so this is the time. So you destroy electron and phonon and create a new electron with this momentum. Or you can also think of the other term, the b dagger term, is you have the original electron which is in the eigenstate k sigma. This gets scattered into an electron with k plus q plus g. These are all vectors. And you emit a phonon of momentum minus q lambda. Now you can see what this interaction does. This interaction conserves momentum only up to a reciprocal lattice vector. This should not come as a surprise because this interaction is electron interacting with a periodic lattice. So the momentum of the lattice is only conserved up to a reciprocal lattice vector. Go back to our discussion for these periodic systems of Brillouin zone, where we showed that a block state with wave vector psi k and a block state with wave vector psi k plus g, where g is any reciprocal lattice vector, has the same physical information. So this should not come as a surprise. In fact, it's a consistency check that this interaction, the electron-phonon interaction, conserves momentum only up to a reciprocal lattice vector. So this is so far so good. We have general form of electron-phonon momentum. Let me just say one last thing and then we'll continue tomorrow. So our goal is to develop an interaction or to consider interaction between electrons mediated by phonons. So what you can do is look at this diagram, and what if you have one electron that comes in and a phonon coming in, and this is the outgoing electron. What if you join these two? What if this, so consider an interaction where you have an electron coming in, electron going out, and there is one phonon mode, and so you have two electrons coming in, two electrons going out. This is the first half is this. So electron comes in, it scatters into another electron and emits a phonon. The other electron absorbs this phonon and scatters into another electron. So if you integrate out phonons, you can, so this is an effective description of electrons interacting with other electrons, two-body interactions, mediated by phonons. So our task tomorrow is going to be investigating this object in detail, and I will try to show you that this interaction is very different from the Coulomb interaction that we saw, which is repulsive for electrons. Under some constraint, this interaction can be attractive, and this will give rise to Cooper pairs. Thank you. Any questions? So we'll continue tomorrow.